So it's my great pleasure to introduce Dorette Pronk, who will today tell us about lax colimits and fibrations of double categories. Take it away.
Okay, thank you. And thank you for Bryce and Tim for organizing this workshop and bringing us together and giving us this place to share and connect. And so it's been very interesting this week. And so I definitely hope that we will have more, have sequels of this meeting, either virtual or in person. So again, thank you. So I'm going to start by again of setting up the background. Well, let me first say who my co-author is.
Very sorry to interrupt you. The video is mirrored on your share screen.
Oh wait, sorry. You mean that?
Yes, perfect. Thank you.
Thanks. I forgot to remove that. Let me just start by saying who my co-authors are on this project. Well, it's actually two papers that are working. Well, one is finished, the other one we're almost finished. And this joint work with Jeff Grotwell, Michael Lambert, who will be speaking later this week on something else but related, and Martin Shield and Margie Bayer. And so the first paper has already appeared in TAC, and the other one is almost finished, hopefully done before Christmas. Not published before Christmas, but at least written. So let me quickly remind people about the Grothendieck construction. I'm basically only going, the first slides are all stuff that we have been talking about the whole week already, but I just want to set my notation and kind of give the background of how I want to look at things. So the Grothendieck category of elements can be characterized in two ways, either as a lax or some people call an oplax colimit of a diagram in CAT, and or as the object's functor, well, the object's part of a functor that gives an equivalence of two categories, depending on whether the original functor that I'm looking at here, this one here, is a covariant or contravariant functor. I would get an equivalence with fibrations or co-fibrations. So if the functor is covariant, I get co-fibrations. If the functor is contravariant, I get fibrations. And I want to look at both aspects today. So I mean, both aspects is in the lax colimit aspect and the fibration aspect, but now for double categories. I want to also quickly review fibrations because I need one piece of information there. If we look at the, I can look at the category of well, first fibrations themselves. Fibration, as we've talked about already earlier this week, has always a cleavage because we have these Cartesian arrows and we can make a choice. And a cloven fibration would be then a fibration with a cleavage. And a cloven fibration will give me an index category. And coming back with the Grothendieck construction, we do get a natural canonical cleavage coming with that. So why do I focus on that for a moment? Well, if we look at morphisms between fibrations, then we always ask that they would preserve the Cartesian arrows. Asking that cleavages are preserved is a very strong condition to have. But sometimes you need that, because without asking for that, you cannot construct pullbacks in the category of fibrations. And so for that reason, what I will be doing today when I look at fibrations is that I will assume that I have chosen a cleavage for each fibration. And so the same fibration may show up many times. But then I will have the category of fibrations, the morphisms do not preserve the cleavages. So they're just Cartesian morphism preserving. And CFib is the one that where the cleavages are preserved. Just one little piece of information here. And then the equivalence between index categories and fibrations will restrict to an equivalence between CFib, so the category with cloven fibrations and cleavages preserved, and ICATs, but now with strict natural transformations instead of the pseudo natural transformations that we have in the other case. So keep that in mind when we go on. Okay, well, one more time introduce the double categories, and only because I again want to say what my horizontal and my vertical arrows are. So for me, the horizontal arrows today will be as Bob Perret does it. So the what's the arrows inside C naught, and we also sometimes call them inner arrows, or arrows as other people have called them, and then the pro arrows, or I sometimes like to call outer arrows, are going to go vertical, and we have double cells as normal. And then with the, so and I will use D0 and D1 for the domain and codomain inside the categories building the diagram, and source and target for the outer part of the diagram. Just as a reminder, any two category can be made into a double category either via the quintet construction, or in a horizontal way or in a vertical way. We've seen these a couple of times too now. And again, they're going to come back in a bit. One other thing I want to kind of add there is that we can also adjust our quintet construction a bit, which can be very helpful. If you have a two category with a distinguished family of arrows sigma, then Q sigma of C will be the double category where I'm assuming that the horizontal arrows are taken in the smaller class. And there are a number of examples of these that are actually not strict, not all of them at least. So if you can, for rel, we have functions and relations. And so sets as objects, obviously. If we take prof, we have functors and pro-functors. The only issues, of course, the pro-functors are not associative in composition. So in a moment, I'm going to talk about as fairly in the pseudo double categories, span cats and ring, all similar idea. So in those last examples, we need pseudo double categories, and at least for half of this talk, we will work with pseudo. The other half of the talk we're doing with strict for the moment, although I think that it can all be extended to pseudo, but we haven't done it. Pseudo double category, we just take the diagram with the two cells in there. So because cat is in two categories, so we can do that. And so now we have, of course, more examples still. And so just be aware that when it comes to composition, our horizontal composition is strict, vertical composition will be pseudo. Okay, now I am going to revisit double functors and want to point one thing out. Whenever we actually looking at a two category K, we can that has two pullbacks, and instead of cats, we can take cats inside of K, and we can consider lax double functors. And the point is that if we take lax double functors, we ask that composition and identities are preserved up to a two cell, going in the direction indicated. But source and targets, we do not put any two cell in there. So they need to be preserved strictly. And again, this is so that when I come back to that, you see where that's important. So now I'm coming to a slide where I want to indicate that we have a problem when we want to think about indexed double categories. And so double cat itself has objects, arrows, one flavor, only double functors. with transformations in two flavors, horizontally and vertically, and with modifications. So double cat itself is not a double category. And so like two cats can be viewed as a two category, and cat can be viewed as a category, and which makes things nice for indexing, but double cat doesn't. So what double cat does have going for it, it's enriched in itself. And so, but when it comes to indexing functors, we need to find a different codomain. So if we have a diagram indexed by a double category, and we want to use double functor as our indexing functor, we need to find a new codomain for that. And so we have two options. Option number one is to use spancat, which is a double two category. And it's a pseudo category in the two category of two categories, two functors and two natural transformations. The arrows, so that is the horizontal parts, are just the arrows in K. If we do it for span K, do it more, it's slightly more general because I need a couple of times not just span cat but some span of other things. Vertically, we're using spans, and then double cells are what people have used before in this conference. And then we also have two cells between them where we are asking for a triple of two cells in the surrounding category, okay, but that's satisfy the cylinder commutativity conditions. So if I compose sigma with r primes, that's the same as composing phi with r, and similarly on the bottom of that diagram. Turns out, if you take a lax double functor from the terminal double category, so 1, to span cat, then you get precisely a double category back. And also monads in this thing are nice and understood. And so this is a good indexing, a good codomain for an indexing functor. The other option, so when we want to do fibrations, that's going to be the right thing to do. But we were also thinking about the colimits. And actually, I started this project with Margia because she was looking for a notion of colimit for double categories that was involving both directions of the arrows, horizontal and vertical. And because she had a topological example in mind. And so we were trying to find a double category where the objects are double categories. So, well, we have seen that double cat was enriched over double cat, but we also know that we can think of double categories, the category of double categories as a two category in two ways, horizontally or vertically. And then we can use any of our three functors to come back to double cat, either vertically, horizontally, or with quintets. So we're going to opt for the last one. And it doesn't really matter whether you go horizontal or vertical. Well, it matters if you, I think if you do pseudo, but when we started originally with strict double categories, it didn't matter. And so we took V, and today that's actually one reason why my pro arrows are going in the vertical direction, so that that all works out, so that the two constructions you will see in the end, that in, let me just give the punchline away, well, part of the punchline, and that is that this second case becomes a special case of the first case, but only in terms of fibrations. The special case that we get in this second situation does give us colimits that I don't know yet how to do in the first case, although we have some ideas, we're working on it. But so let's go to the first situation. So first of all, then, when we're aiming for double fibrations, we need lax pseudo double functors into span cats. When we're aiming for double lax colimits, we are going to look at these functors into Q double cat V. And we will, just for ease of notation, because this gets painful to write a lot of the time, we call them vertical double functors from D into double cats, but they're really double functors into Q double cat V. Okay, so let's do the first case first. So we're going to look for a Grothendieck construction for the indexing functors from D to span cat. So we have, when we have a functor like this, a lax double pseudo functor, we get a pair of pseudo functors into cats. The first one is easy to see because the zero part of span cat is just cat. So we're right there, the objects. For the arrows part, we had the span cat one, but now we can take the apex functor into cats. So what we're doing is we had our diagram for a double cell. We're just going to take the middle part there. And that gets me into cats. We can even have the natural transformation between them here. And I can apply the Grothendieck construction for each one of these two functors. So we get an elements category for F0 and for F1. Elements for F0 give a vibration over D0. For F1, you get a vibration over D1. And then they form now together the objects and arrows for a double category that we'll call elements of F with a double vibration into D. Well, we haven't defined that yet, but that's my next slide. So, so in what sense is this a double vibration? What does that mean? So before I do that, actually, before I define what the double vibration is, I'm just going to first look at what's this, what is the result of doing elements here and what kind of functor do we have here? What kind of double functor? So just to remind you, when I'm taking a pro arrow or a vertical arrow in D, the image is going to be an outer arrow in, so a span. And I will call the span FM, but the object FM, and then LM and RM for the two parts of the span, so left and right. Then if I just use that notation, then I can say that the elements of F have inner arrows, just pairs as you expect them in the Grothendieck construction. And outer arrows are going to be a pair of an M in the indexing category together with an object M bar that sits in FM. So it becomes a pair of an arrow with an object. And the object needs to be chosen such that if I apply the functor LM to it, I get X for the X that was in the domain, and I apply RM to it, I get Y, the Y from the codomain, yes. And then the squares of the elements construction become pairs theta, theta bar. The theta bar is now an arrow in FM, which is again feeling like a Grothendieck type thing. So we have the theta, this is square in D, the theta bar, so theta gives you a chance to take, because remember, then you can take a theta upper star, which is F theta, which is an arrow, because it's the arrow in the middle of that square for the spans. And I can take a theta upper star there, and then LM of theta bar has to be F bar, RM of theta bar has to be G bar. It's the same kind of thing going on. So this has on a projection down to D, just going to the first coordinates, and this is what is we'll see as our canonical example of a double vibration. So what is a double vibration? When we started out thinking about that, and the first suggestion was, hey, let's take a category object in Fib. Problem, fib doesn't have all the two pullbacks that we need. And also, if you actually do that, you realize that you're asking for the same vibrational strictness for source and target as you're asking for identities and composition. And that's not right. We know that that's not what we want for double functors. So a double vibration needs to be a pseudo category in CFib. Well, sorry, not in fib, but such that source and target are in CFib. So there, for source and target, we want the stricts. And then that ensures that you also can take the pullbacks that you need to take in order to do composition for your category object. So they need to preserve the cleavages. So when we do that, an equivalent way to phrase this is to say that the double vibration is a strict double functor between two pseudo double categories. So this is just kind of like, are you looking at the diagram horizontally or vertically? So if you look one way, you have an category object in fib. The other way, you're looking at a functor. Such that P0 and P1 need to be vibrations in the usual sense. They have and they need to admit a cleavage such that source and target become cleavage preserving. And for the rest, for, as I've said, identities and composition only need to be Cartesian morphism preserving. So that is then a double vibration. And let's look at a couple of examples to show you that you have seen these already in various places. If we take E0 and B0 to be both 1, so take the objects categories to be just the terminal category, we get monoidal vibrations as defined by Schulman. If we take a 2 functor and then P is a 2 vibration as defined by Buckley and earlier referred to today as well, if and only if the quintet applied to P gives me a double vibration. So, so they nicely generalize 2 vibrations. If P0 and P1 are discrete vibrations, then we get the discrete double vibrations from Lambert. And the Grothendieck construction that was given by David Meyers, he actually gave 2 double Grothendieck constructions in his paper on dynamical systems. And one of them is easily seen, right way seen that to be a double vibration. The other one is too, but I'll say more about it at the end. A couple more examples that are more double categorical. The domain functor is a vibration. We have an image from span to rel, gives a double up vibration. There's a split double vibration for fem. And the codomain vibration is a double vibration if we have a couple extra conditions there. Now, remember, double cats is a 2 category, and we could also ask ourselves, well, what are the internal vibrations a la street? And we have actually shown that a strict double functor is an internal vibration in double cat, if and only if it's a double vibration. And so pay attention, double cat, this is double cat with pseudo functors, but we ask that the strict, that the functor I'm looking at is strict. So this is, you can look at pseudo double functors, but then we need to look in double cat L, so with lax functors, and then this becomes a pseudo, this becomes a vibration if P0 and P1 are vibrations that emit cleavages preserved by SE and TE. It's also a pseudo double functor is an internal vibration in double cats if we further require that identity and tensor are Cartesian morphism preserving, and a strict double functor is an internal fibration in double cat with strict functors, and this kind of follows from the above by just requiring everything to become strict. That means that all the cleavages now need to be, all the maps have to preserve cleavages. Okay, so now how about the correspondence, the second part of the Grothendieck result about being indexed versus fibrations? Do we get all fibrations this way? And the answer is yes, there is an equivalence of categories between double fibrations and indexed, so functors into span cat. And the way to see that is to first say, okay, we start with the traditional one. We restrict ourselves to CFib and ICATs with the strict transformations. Then we can take span over both of those. And then we lift with the same technique that was used by Joe and Christina in their paper in 2020 to get the results via the monoidal fibrations. I'll leave the story for another day or go read the paper. One thing I want to say is that going from right to left, so the Grothendieck construction is an extension of what Paré did in 2011 and is also an extension of the second half of what I'm now going to talk about. So the other way to do this was, well, let's look at functors into Q double cat V. And you may have some concerns because you might be like, what happened to the horizontal part? Are you really going to be able to say something about horizontally and vertically? And the answer is yes, although I have to be honest, vertical does get some preference here. But horizontal does get a role to play, and we'll see how what kind of things it can do. And this is being taken care of by a new notion of transformation. So our vertical double functors, which were double functors into Q double cat V, can get a new notion of transformation that is not just a horizontal or vertical transformation, but that takes both sides into account. And what we're going to do is we were inspired by Benabou's cylinder construction for defining transformations. So that is the plan. I will define a cylinder double category, and we had a choice here. We could have done H or V. We chose for V. Basically, because of the vertical double functors, that is how things will nicely go together. So we'll see that we have from these vertical cylinders, we'll have a domain and a codomain functor into double cats that are vertical. So they're really functors into Q double cat V. And doubly lax transformation is then given by a functor into the cylinder category, just like Benabou defines transformations for bicategories. Okay, so first the cylinders. A double category of vertical cylinders is defined with objects double functors. So I'm just going to draw them vertically. A vertical arrow in this double category of cylinders is given by a square with a vertical transformation. So this is a square of double functors and a vertical transformation to fill that. A horizontal arrow in the cylinders is given by a pair of double functors and a horizontal transformation. Now a double cylinder, ready for the big picture. So we have here on the corners are 4 objects with our double functors drawn vertically. That's those 4. And then we have the vertical transformations one F to F bar sitting here, and this one here sitting here. So those are the vertical arrows. Then there's the horizontal ones sitting here on the back and the front on the right. And then for the rest of the cylinder, we get a vertical square on the top and the bottom. This is why they're called vertical cylinders. And because that's what we want the domain and codomain to be in the end. They need to be vertical functors. So they get their vertical parts. And then there is a modification sitting on the inside. Now the vertical cells that we had over in the front and on the top, so this one and that one, they compose, and that gives me this set. And then the ones on the the other one, of course. And then the other two give me this one. And then we have the two horizontal ones, and that gives me precisely the space to put in a modification. So a whole cylinder consists of a modification with those sides and the top and bottom. So as I said, there are vertical double functors D0 and D1 from the cylinder double category into double cats, and a doubly lax transformation between vertical double functors is now given by a double functor from D into the cylinder category, such that, of course, D0 is F and D1 gives me G. So what do I need to define a doubly lax transformation? Just to kind of recap. I need to give for every double cell in the domain an cube, so that everything fits together as given here. So we see that if I look at this part here, it gives me the bottom part here, and this composite here gives me that one here. Those are all double functors. That's why they can be composed at the end of the day. And theta alpha is the modification inside the cube. Okay. Takes a bit more time to really digest this, but I'll leave that for another day. So if F and G are two vertical double functors, lax transformations are represented by double functors, which means that I have horizontal and vertical transformations between them and the modifications. So I have a whole HOM double category that is sitting inside the double category of double functors, etc., from D to the cylinder double category. And so of course, only the parts that has the right domain and codomain at the top and the bottom. Okay, so let's see how this generalizes concepts that we have seen before. And it's kind of nice because you'll see that here again, double categories can encode a lot of information from different places. So if I take a two category B and I see that my HOMs are categories, so I can apply the quartet construction, I get a double cat enriched category, what I will call Q hat of B. So this is doing locally quintets. And that allows us to look at lax transformations between two functors as a special case of our new doubly lax transformations. And basically, you recover the cylinders a la Benabou. Now I can restrict the Q on the codomain and taking only particular class omega of two cells of B for the horizontal arrows. So remember, locally we have the arrows and the two cells of my two category B. And if I only take a particular class, then I will get, I can look at a restricted class of transformations in the double category case. If I restrict the Q on the domain, then I can get what we call the sigma transformations that also had occurred yesterday in John Burke's talk. And we can combine the two, of course, as well. So our goal was to look at colimits. And so we want to look at what are doubly Lax co-cones for a vertical double functor. Well, we would have to just look at the doubly Lax transformations to a constant double functor for any given vertex E double category. And so we end up, remember, the home was a double category. So we have a double category of doubly Lax transformations and every other structure in between them from F to delta E. And when is this then the doubly Lax colimit? If it, well, when we get an isomorphism of double categories between the home double category from L to E. So L is my candidate colimit, E is some other double category. And if we have an isomorphism between the home from L to E and the induced composed by lambda map into looking at the cones from LC to E, from F to E, sorry. And our claim is now that this doubly Lax colimit can be obtained by a new double Grothendieck construction. And to indicate that this is a different one from the other one, I'll call this one GR, where the other one was called elements, just so that we keep the two separate for now. So in this case, we will be playing Grothendieck on both directions slightly differently from the other one, but they are related. So the objects are what you expect, I hope, at least. For vertical arrows, we do also what you would expect, a pair of vertical arrows, and one in the indexing category, and the other one in the image double category. Horizontal arrows, same thing. So horizontally and vertically, we are doing just the same, pretty much the same thing. We have to do the work on the double cells to make everything fit. So that's why we have a good look at things. So for double cells, the first coordinate is just an ordinary double cell in D. But for the second coordinate, you have to kind of grab all your pieces together and make sure that it fits. And so the alpha will give me an F alpha X, a vertical arrow, from FFX to FUX. All the way, because alpha is, F alpha is going to give me, 1 second, I'll draw it like this. F alpha is a vertical cell, remember, a vertical cell for FF, FV, FU, and FF primed. So just to remind you, because we're going into Q double cat V, this is a vertical cell, which means that I have a vertical arrow like that. And so this is the piece that's going to make everything fit together in the end. So after that, it's a matter of, okay, this is what you kind of usually would expect in for Grothendieck type things. This is also, except that of course you get horizontal and vertical to combine, but that's precisely where we put our phi, our second coordinate. So this is the part that feels at first a little like, oh, is that all going to compose? Well, they are composing horizontally and vertically. What I want to say here at this point is just, I want to talk quickly a little bit about factorizations. On the horizontal and vertical arrows, we get the typical factorization of with a Cartesian arrow and an arrow in the fiber. And Now on the double cells that happens too, except that we have these two extra pieces sitting here. We have these identity cells that just are needed in order to make everything fit, to get the square. But other than that, these here are the typical kind of factorization that you would hope for. And I think personally that there is more to be done here to study those factorizations and look at factorization systems for double categories. We haven't done that yet. Would be happy to share with others and let people think further about this. So our main theorem, well, the first main theorem is that for the colimits, the doubly lax cocone that I get with delta of the Grothendieck construction is indeed the required colimit. And furthermore, we have locally an isomorphism of double categories between the home between two vertical functors, vertical double functors, and on the other hand, the maps between the Grothendieck constructions over D. So that's kind of promising because it says, okay, if you can identify what your image is of the Grothendieck construction, then you would have another notion of fibration and you would have a correspondence. So that was our next task, but before I talk about that, let me first give a couple of applications. So kind of show you that these colimits, again, are extending colimits that we have seen before. First of all, I can look at the colimits in two cats. So if I have a two functor from a two category A into two cats, we can construct a double index functor out of it in a couple of different ways. And the first one I want to look at is to compose with V to, and I'm going into double cat and I will think about it as a two category with, again, the vertical transformations. And now I can apply V again. So this was just to send two cat into double cat V, but now I'm going to apply V to the whole thing so that I get VA as a double category, because I actually want my domain now to become a double category. So, and do the whole, and so I get VA, sorry, not the whole thing. I go up to here, and then I take the inclusion into Q double cat V. So we have this here, we apply V to it, we get that, and then we take the inclusion. If you apply here our double Grothendieck construction, we get the V of the Grothendieck construction as given by Buckley and earlier by Bakovic. And now further, so I think that this was originally given just as a fibration. And now we can say, well, but wait, V is actually an isomorphism of three categories, sorry, between two cats and its image in double cat V. Which means that our colimit results tells us that this one here, oh, sorry, without the V, is also, it's a lax tricolimit in two cat, or oplax if you prefer. But it's, so this gives us that Buckley's construction is also a tricolimit. Let's look at categories of elements. If we have a functor from A into Z, then the colimit of the diagram is pi naught of the elements construction on the composite of D with F. D is just the inclusion from Z into cat, sending Z to a discrete category. And this is actually an exercise that I tend to give to my category theory students at the end of the semester. So it follows from the universal property of the elements construction as Lax colimit by applying it to cones with discrete categories and using the adjunction. Well, we can apply that same paradigm between cat and double cat V and used V and the pi naught, the quotient in going. Pi naught is basically take quotient with respect to the horizontal arrows and cells. So take that quotient. And then it follows from our main theorem that if I take pi naught of the Q of V after F over HA, we get the strict two-categorical colimit of F. So we can get the Oplax one as a tricolimit, and then we have the strict two-categorical colimit as well as a special case of what we have here. And this is actually the elements construction of Paré. And I'm wondering whether I have that date here correct, but I'll leave that for now. Okay, so I want to come back to David's work. So the double categorical read product that was given in the dynamical systems paper, if I can get that one as our construction as well, by taking a functor from A up to cat, we compose with Q. We then need to do a horizontal flip and apply Q to all of that. It's a bit of a construction. You need to kind of really sit down and work out the details, but that gives you precisely the read product of F with F op as introduced by Myers. And we wrote down here the diagrams. So this is our diagram. This would be David's diagram. Okay, so then the last question. So what are the functors that we get by doing the Grothendieck construction to one of those indexing functors? And it's a bit of a mouthful. I apologize. I need to still think about a nicer way to summarize this. But so basically what it comes down to is we get a functor between double categories, Grothendieck construction of F to D, which is an op vibration on the vertical arrows, an op vibration on the horizontal arrows, an op vibration on double cells with horizontal composition. So we take basically vertical arrows as the objects, double cells as the horizontal arrows, and then horizontal composition. That gives us also an op vibration. And then the fourth part, now you might wonder, okay, what happens in the other direction? What if you take double cells with vertical composition? Well, here we have to restrict ourselves to only the part that sits over horizontal identities. So we only take the fiber part there. So if you take the fiber part in the vertical direction, there we do get then again an op vibration. And finally, we have to require that these guys all together have cleavages that are compatible in a suitable sense and are split horizontally and vertically where needed. So basically it comes down to we get almost everything that you could think of to be a vibration except for the vertical the vertical composition of the cells. There you only ask it for the fiber part. And so we can then look back and say, okay, that was kind of a mouthful. Does this generalize anything? Yes. So the functor, so a functor is two functor between so for a two functor between two categories, P is going to be a split two co-op vibration as in Buckley, if and only if VP is an HV split co-op vibration. So V it's the V part now that gets carried over, and I suspect actually, so remember we were doing this all strict. I think once we go to pseudo, that we can get rid of the split part and get a more general correspondence. So then we indeed get the correspondence that I was announcing, that so now we have an equivalence of categories between index categories and these new fibrations. And if you're wondering how the two fit together, I am running out of time. Let me just quickly say a little bit. There is actually a double functor from this indexing category to span cat. And it's pretty much what you, well, if you think about it for maybe a half hour or so, you would come up with it. If you're played enough with span, the idea, the main idea is really to take this guy in the middle. And that's a Grothendieck thing again, because these are just objects of x naught together with an arrow. Let me do it a little longer. So an x in x naught together with an arrow from chi naught of x into some object in y. That looks a lot like something Grothendiecky, and in this vein here, and then you just take the projection on the first coordinate and t after pi 1. So take the y here for the second part. So that gives you, and then on the double cells, you just have to think for a bit and realize what needs to fit there in the middle. It's basically the only thing that can fit there, and then it works. And so that means now that any indexing functor in the second part of my talk generates an indexing functor in the first part of the talk. And the Grothendieck construction actually is the same. Yes. So, which then means, well, we could also see already that we had a special kind of fibrations here. These fibrations in the second half of the talk were a special case of the first fibrations. And the only question is now, we had the double colimits in the second half. What kind of colimits could potentially fit with the first half? That's our next part that we first want to work on. And there are other questions to ask, like, I'm curious actually for David Jasmeyer's work. Does it tell us more about the constructions that he has made there and their role in dynamical systems to know that they are colimits, so they can be seen as fibrations? That's something that I would love to hear from others about. Thank you.
Okay, thank you very much. And are there any questions? Feel free to jump in. Does this double functor S admit any adjoints?
I constructed it last week. So
Okay, okay, so that's a bit.
I have not thought, that's a very good question. Yeah, that would be very handy, of course, because that would give me a chance to go back in a different way. So let's say this way, I did not immediately see any way of going back when I was looking at it. I was like, oh, the easier way is to go this way. But now that the question has been asked, I'll have to think about it. This was the quick way to go. Let's say that way. That's
okay. But it's a strict double functor or a lapse.
Yes. No, this one is strict.
Okay.
Well, actually, no. Be careful here because span cat is pseudo. Q double cat v is strict. So probably pseudo. Okay. I just haven't thought about it further yet. I was talking with Martin last week, and we're like, if I give this talk, I need to at least have some kind of connection at the very end. So. But we think that the fact that we have these that we can characterize double categories as maps from one into span cat should help us to get the colimits, get some kind of colimit aspect on the other side.
Right.
We just haven't had time to work that out. And maybe once we know what kind of colimits we get there, that might also indicate what kind of functor we may want to put in the other direction.
And this this cylinder double category that you construct, does it have some kind of universal property associated to it?
That's a good question.
I mean, in some sense, it's classifying your doubly lax transformations, but that you sort of use that as your definition rather than.
Yeah, no, I should think about it. So it is a monoidal double category because you can also stack them vertically, of course. It's like you for what we're doing, we only need to stack horizontally and so on. But you can, so it's monoidal. Yeah, I don't know right away, but I mean, it feels kind of like some type of arrow category, but
Right, yeah. Okay.
Because our cylinders are really cubes. So
Yeah. Are there any other questions from the audience?
And of course, I'm curious now with everything I've seen this week, how this relates to what other people have been working on. So, yeah.
Could I ask a question? Sorry, my voice.
Yes.
I mean, a great talk. It's just that, I mean, now that you are so fluent in these fibrations, I was wondering if multi-op fibrations might have a place in your framework. So do you have any indication that could be something interesting in your double categories? Or
I'm afraid that I don't know enough about multi-op fibrations yet to be able to say that right away. That is a good question. Maybe if you know more about them, then we should talk together and see what we can do.
Yes, anyways, we should talk.
That sounds more like a good joint project.
Yeah, maybe. And sorry, then maybe the more conservative question would be about street of fibrations, because is there any, I mean, you spoke about Grothendieck of fibrations, if I understood correctly, mostly, no? And I mean, double categorical.
So the street fibrations fit in the first part. So they are precisely there. So if I go back up, I know I mentioned a lot today, so this was really a combination of two talks. No, it's I feel more sorry for you guys. I threw a lot at you. I was like, I got an hour. I was like, oh, I can say more. 1 second. Where were we here? One up here. Yeah. So the street fibrations are precisely the internal fibrations in double cats. So strict double functor that works directly. If you work with pseudo double functors, then it's be a bit careful. So it's an internal fibration in double cat if we have a couple of extra conditions there. But so it's a matter of check who needs to be Cartesian morphism preserving, who needs to be cleavage preserving.
And sorry, one more kind of challenge question, but maybe that's a bit out of the scope. Assume I mean, because I mean, that's motivated by what we played with, of course. When you have a composition in the weak direction, if the functor of composing cells in the weak direction is a street of fibration, do you have an intuition if that would tell you that you have pullbacks in the 0 and the 1? I mean, we have a suspicion this might be the case, but you will presumably see this immediately.
So I think the answer is, so wait, so you had, what was your assumption again? Sorry, because I think
my assumption is that you have a pseudo double category and that the composition, the functor that composes in the weak direction, I guess in your case, it's the vertical direction, yes.
Yeah.
That is a functor called H2, this the vertical composition, and say this is a street op vibration. Would that imply anything interesting regarding the existence of pullbacks on the 0 and the 1? I have this weird feeling you have some nice interactions between these vibrational concepts and existence of limits and so on.
Yes, but I don't dare to answer it without doing a little calculation there.
Okay, yes, okay. So
that's
yeah, so maybe we can meet next week.
I don't have it right away here because I just need to make sure that everything fits in the right place here.
Yes.
But my first hunch is yes, but I would have to do the calculation to check.
I mean, that would be fantastic because I mean that would answer a technical question we had.
Okay, so maybe if you send me an email to remind me,
yes.
then I don't mind at all doing the calculation, but rather
fantastic.
Not right. Yeah.
Yes. Thank you very much. Thank you.
You're welcome. Thanks for the interest.
Okay, I think we should thank our speaker again.
Thank you.